The TI-83 and 84 series of graphing calculators allow users to write and run programs directly on the calculator using a language called TI Basic. It provides operators like if, else, and while. It is quite fun, but it is fairly limited in speed and capability. TI Assembly allows users full control over the calculator. An assembly language is a programming language that corresponds very closely with the machine code instructions the CPU runs. These calculators take it a step further by making the user literally input raw bytes. Because there are no mnemonics or comments to help make sense of what you're typing, it's easy to make mistakes and crash your calculator. If your calculator freezes up, you can reset the operating system by taking a battery out and putting it back in. This will clear the RAM and delete anything not saved in archive. Archive your data before assembly programming. Also, because of this direct usage of calculator hardware, an assembly program on one calculator will not necessarily run on a different calculator. The programs I write should work on any TI-83 Plus and maybe the TI-83, but not other calculators. Let's write an assembly program that simply says hello. In TI Basic, we can use the disp command to display hello. It's easy to code, but we can't even print lowercase letters. In assembly, we can use any of the instructions the calculator's processor is capable of running. For the TI-83 Plus, that processor is the Zilog Z80, a relic from the 70s and 80s, perhaps most notable for powering the Pac-Man arcade machine. My favorite reference for the Z80's instruction set is at clearhome.org. Here, the instructions are given using common assembly mnemonics. There are output instructions, but interacting directly with the screen driver is well beyond the scope of this video. Luckily, the calculator's operating system has several routines for printing to the screen. The TI OS makes these available to user programs through an interface called B calls, which are similar to normal function calls. Brandon W's WikiTI has extensive documentation on all of the B calls we can use. Searching around, we find this putS B call that displays a string on the screen in the large font. Perfect. Many of these system calls require inputs to be set up. Cur_row and cur_call are locations in memory where the calculator keeps track of the cursor's position. When we go to run our program and we hit enter, the cursor will be at the start of the next line by default, which I think is a great place to print our string, so we won't touch these. The next input is HL, which is a pair of registers in the Z80. Registers are little memory cells that a CPU works with. In the Z80, H and L are often used together to store a 16-bit value, usually a memory address. The B call wants HL to hold the address of a zero-terminated string, which is a string of characters followed by a 0 byte to mark the end. It expects the string in ASCII, so hello will be encoded as 48, 65, 6C, 6C, 6F21, and a terminating 0. The instruction for loading a value into HL is 21, so our code will be 21xxxx, where xxxx will be the address of our string. Now we can call putS. For B calls, we use the reset28 hex command, EF, and then put the 2-byte B call address. In this case, it's 450A, except we actually have to switch the bytes around since the Z80 is little endian, making it EF0A45. This program will print the string pointed to by HL. But if we end our program here, the CPU will just keep executing whatever comes after our program in memory, which will most certainly cause a crash. The operating system runs our program like a function. So when we're done, we use the return command, C9, to hand control back to the operating system. Now, the CPU won't execute anything that comes after. This is a great place to put our zero-terminated string. The last piece of the puzzle is figuring out what address our string is at. When our program is loaded into memory, it starts at the address 9D95. The second byte is at 9D96, then 9D97, 9D98, 99, 9A, 9B, and finally, our string starts at 9D, 9C. We will flip the bytes again to make the first instruction 219C, 9D. Now, we can run our program with the asm command. And it says hello. We can also edit the string as we please, as long as the string still starts at 9D, 9C. Now, let's take a look at this quine. How does it work? At a high level, it's simpler than you might think. Normally, the challenge with a quine is that your program's source code is translated into machine code, and the machine code must somehow recreate the source code it came from. In assembly, your source code is the machine code, and it sits in memory exactly as you entered it. The program just needs to be a print function that prints values from memory to the screen as hexadecimal numbers instead of ASCII characters. To make it a quine, it starts printing from where the code starts in memory, and it stops at the end of the program. There's only a few variables to keep track of over the course of this program, so we can assign them all registers. Register pair HL is often used for holding addresses, so we'll use it to hold the address of the byte we're printing. To print characters, they need to be in the A register, so we'll use A to hold the values we're printing. But the values in memory aren't exactly what we print, since each byte needs to be converted into 2 ASCII characters. We'll use the B register to hold the values we copy from memory, and then the A register will copy from B and do all of the transformation maths. The C and D registers are free if we need them. We'll start by just printing 1 byte. First, we load HL with the address where our program is in memory, which is always 9D95. Then, we load B with the value HL points to. Now, we have the value we want to print, but we need to print it as 2 ASCII characters, one for the value of the upper 4 bits and one for the lower 4. Originally, I had the same code twice, just slightly modified, but I figured out a space-efficient way to do it with a loop. We'll use the C register to keep track of the loop, and we'll load it with 255 to start. Now, we'll copy our value to the A register so we can start messing with it. We print the upper 4 bits first, so let's call a system function to shift the upper 4 bits to the lower 4. Next, we mask out the high bits. And now, we're left with just the value we want to print. Right now, it's a numerical value, so we need to map it to the corresponding ASCII character's value. First, we add 48. Now, the values 0 through 9 work, but the values 10 through 15 print random punctuation instead of the letters A through F. We'll check if our value is bigger than 9. If not, we can jump ahead to printing. Otherwise, we add an additional 7 before printing. The print command is another call to a system function. For our little loop, we increment C and loop if it's 0. The first time through, C is 255, plus 1 overflows to 0, so we run the loop again. The second time, though, C is 0, plus 1 is non-zero, so the program continues. We can't jump all the way back to loading A with B, since we'd shift the upper 4 bits and just print the same thing again. Instead, we load A with B ourselves, and then jump right back to where we were after the shift. Here's where we increment C, and jump backwards if it's 0. The second time through, we mask out the high 4 bits, convert to ASCII, and print the hexadecimal digit for the lower 4 bits. Once we've printed a byte, we increment the address to print from. If we unconditionally jump back to the top, we'll keep printing bytes forever. To mark when our program's over, we end it with a 0 byte, and we'll check to make sure we haven't hit this 0 as we keep printing. The quickest way to get a 0 to compare to is by XORing A with itself. Now, we can compare this 0 to the value in the B register. If they're different, we'll jump back to the loading and printing. Otherwise, we've reached the 0 byte and the end of our program, so we return control to the operating system. Now just add a 0 byte to mark the end, and our program is finished. If you couldn't tell, I spent a fair amount of time optimizing this code to be as short as possible. While making this video, I managed to further optimize it from 34 bytes down to 32. I'll go over those optimizations and a few tips for anyone interested.